Here's a video about using the quadratic integrate and fire implemented in a field programmable analog array to create an analog XOR function. So let's first talk about each quadratic integrate and fire neuron. It consists of a multiplier, and you want to use the fastest clock you can, and this clock ratio you have to keep as set. You have this is an input voltage of 2, which then here gets scaled. So in this case I have the gain of 1 coming from the integrator node. This 0.125 times 2 creates a positive reset condition when I click non-inverting. If I wanted a negative reset inverting, I would click inverting. Alright. This is the integrator, and I've made it as slow as I can make it because you've got to keep the thing slow for the multiplier to keep up. But notice this one, everything's non-inverting, and the reference voltage is 1. That's V peak. Okay, and V reset is set by 2 volts in this case times 0.125 positive, so it's a positive reset. All right, now in this one, in the XOR, you have to invert one of the inputs, and so input 1, which is coming from a square wave, you just set to inverting, same V peak, right? And then you have a pulse. 4 volts is really 2 volts input. This one's at 250 hertz, 50% duty cycle, all that. And this one is has twice the frequency. All right, and then you have to run it. The green is the one of the inputs, and the purple and blue are the outputs of the quadratic integrate and fire. So there just isn't enough room for another multiplier. So really we have to take the data off the chip. And in this simulation I'm kind of hacking it a bit, where I really would have to take it from here differentially, and then maybe here differentially. So as far as outputs, Scopy could measure it, but I wouldn't be able to measure the inputs. You'd need 2 kits, and I think you can chain them up. But anyway, right now this makes it single. These probes are done so you can look at it single-ended, right? Anyway, you have to save it. You would click save it as a CSV, and then you were done. Now the thing is I could add another chip for the multiply function, but that means I would need another board. And I really don't have that. So what I'm going to do is post-process the multiply in Python. So I read it in. I have to do some changing of the variables so that I can use I can convert things to NumPy array easily. All right, I have my figures. I have so many axes, time, voltage of QIF1, 2, 1 multiplied by the other, and then you can make an inversion by sign. Now you have to use a minus sign because it's actually, this creates XNOR. Alright, so quadratic integrate and fire here, not spiking, spiking. Then this one is spiking, not spiking, spiking, not spiking, right? And so we should have an output high here, low, low, high. And that's what we get. There's some glitches, but that's just like any delay of any XOR gate. Even a digital logic gate will have that kind of thing, and you would use a flip-flop to kind of filter that out. So that's that. Now sure, we could try to, I don't know, let's see. Let's see if we can speed that up. .638. If it doesn't work, it's most likely the multiplier. So that's 1. You'd have to set them all the same. All right, so it should be going a lot faster, which it does, but it no longer looks like a quadratic integrate and fire output. All right, if we zoom in on it, you can see that these square waves are actually what the spikes should be. So it's not really modeling it properly. Okay, and that's kind of why I use the but let's see if 0.01 will work. It's taking a little bit to simulate. You can see it is a mixed signal system where those integrators are actually continuous valued but discrete time. Okay, actually looks like it's working, and so since there's more spikes, I could probably use faster signals, so that's pretty cool. Anyway, this can all be put into programmed into a remote board and tested remotely with Scopy. That's hopefully the next bit.